Right. Hello. Good evening, everyone. I hope you can hear me all right. And then we will start with the tutorial, right? So, Chemeve, right? The tutorial, we will finish that tutorial, right? S block element, that discussion, we'll finish that, complete it and finish it. Then we'll look at some chemical calculation. Question number 53. Yeah. Am I right? Am I in the right place? Question number 53. I said question number 53. Let me look at some of your answers. Yeah, good evening, Dad. Okay. Question number 53. I think that is where we need to start discussing. Question number 53. Right. Okay. Good. Thank you. Thank you. Explain that why the first ionization energy of barium is less than the first ionization energy of calcium. What is the reason? Because of the increase in the radius. Ionization energy mainly depend on the radius. So ionization energy of barium is lower because it has a higher radius, has a higher radius, higher radius than calcium, radius than calcium, So it's a strong, weak attraction, weaker attraction. Therefore, lower ionization energy. Lower I1E. Harid, clear? Magnesium reacts readily with steam. State 2 observations you would make when magnesium react with steam. When magnesium react with steam, what will happen? It gives you magnesium oxide and then hydrogen. So you will see, you can't say hydrogen evolved because you can't see hydrogen evolving out. What you see is, you can see that there's some bubbling that is taking place on the surface of magnesium. So you see bubbling on the surface of magnesium, on the surface of magnesium. And then what is the next thing that you see? There you see this metallic luster is going to disappear and it turns into a white color. Metallic luster turns to a white color, turns to a white color. It disappears and turns into a white color. So that's what happens there. Right. Okay, good. You say write an equation for the reaction. You understand the equation, this equation there. Explain why different observations are made when aqueous barium chloride is added separately to aqueous magnesium sulfate. You have magnesium sulfate and you have aqueous magnesium nitrate. Magnesium nitrate is also there, right? And you are adding barium chloride to each of them. You are adding barium chloride, you are adding barium chloride to this also. When you add barium chloride to this, can you tell me what is the product that you get? Can balan? Magnesium chloride, MgCl2, magnesium chloride is there. And what else? You get barium sulfate is also given. Now you know barium sulfate is a precipitate. Now last week we discussed why barium sulfate becomes a precipitate using energy diagrams, energetics also. We understood that the solvation and the lattice energy, lattice dissociation has a major role in it. Barium sulfate is a good precipitate. You use barium chloride to identify sulfate ions. But if you add barium chloride to magnesium nitrate, you get barium nitrate, all nitrates are soluble. So you don't see any precipitation taking place. Magnesium chloride, group 2 chlorides are soluble. So you don't see any precipitation taking place. No precipitation, no PPT here. But here, a white precipitate is observed. So that is why you see different observations, right? Write the simplest ionic equation including state symbol for any reactions occur. So what is this? Magnesium chloride aqueous and no, magnesium chloride, no, magnesium sulfate, sorry. Magnesium sulfate is what you use. Magnesium sulfate aqueous, and to this you add barium chloride. When you add barium chloride, you get barium sulfate, BaSO4, barium sulfate is given, a precipitate, and magnesium chloride, MgCl2 aqueous. So this is why you see this white precipitate. White precipitate is given there. Terunada. Is it clear? Did you understand that? That was question number 53. Everything is there. The other one, there's no reaction taking place. So therefore, you don't have to write anything. But let us look at question number 54. Read the question and tell me, help me to work on that. Question number 54. Solutions of barium hydroxide are used in titrations of weak acids. Barium hydroxide is a strong acid, strong base. Strong base. Barium hydroxide is a strong base. So you use for titrations in weak acids. State why magnesium hydroxide solution could not be used for this purpose. Why can't you use magnesium hydroxide? What is the reason? Magnesium hydroxide? Why? What do you think? What is your thought? Like you tell me some answers here. Why do you think that you can't use magnesium hydroxide to do this? Some answers. Magnesium hydroxide is not soluble. Yes, not soluble. It's not soluble. And last week we discussed that also. Why magnesium hydroxide is a precipitate using energetics. It is not soluble. Not soluble. Soluble. So therefore, it is impossible. It is impossible to make a known concentration, known solution with known concentration. With known concentration. It's impossible to make a solution with known concentration. Right? Is it clear? Did you understand that? Right. Why there is no reaction occur in magnesium nitrate? Because everything is soluble, so they break back into ions. Like sodium chloride, when it dissolves, there's no reaction, it goes into ions. So if there's a precipitation only, you will see an actual reaction taking place. It's separating out. Otherwise, they are separated, ions. Right? Is it clear? Did you understand that? Right, okay. So, yeah, okay, right. Next one. Magnesium metal is used to make titanium from titanium 4 chloride. This is a reaction you have in your industrial chemistry. So, like, not actually, not now, but several years back, there was this reaction. TiCl4. Magnesium is more reactive, so it gives you magnesium chloride, MgCl2, and titanium is extracted out. This is 2, this is 2. Reaction. Write an equation for this reaction of magnesium with titanyl chloride. Right? This is what the reaction is. Titanium is separated, extracted out. Magnesium burns with bright white light and used in flares and fireworks. Use your knowledge in reactions in group 2 metals with water to explain why water should not be used to put out a fire in which magnesium metal is burned. And that's a very creative question, right? Why do you think? Now you can burn magnesium. The magnesium, when you burn, it gives you a bright flare. Have you burned magnesium? I'm sure you have burned magnesium, right? Have you burned magnesium? At least your teacher has burned magnesium. I'm sure you have seen, yeah? Right? Yeah. Right. Okay. Yes. Good. Yes. You have experience. No. Right. Okay. The flare, okay, sometimes blind, yes, yeah, it gives you like really, really strong flare, right? Bright white flame, yes. So that's the flare that you get. Magnesium plus oxygen gives you magnesium oxide, MgO, right? So this reaction actually takes place. Yeah, this reaction is taking place. And if there is a fire due to magnesium, let us say there's like a big pile of magnesium and it has caught fire. There's a bright white light. They say don't put water to control the fire. Why is that? Don't put water to control the fire. Why? What might happen? If you have water, magnesium, and if you add water, because of this fire, water might evaporate. So it gives you steam. මොකද වෙන්නේ steam? Steam, what happens to steam with magnesium? Magnesium and steam, what might happen? That also reacts. Magnesium and steam reacts. What are the products? Magnesium oxide and hydrogen is evolved. Hydrogen is evolved. Is hydrogen a combustive gas or a non-combustive gas? Hydrogen, if it gives out hydrogen, is it a good thing? Yes, there will be an explosion. Don't you think? Flammable hydrogen, yes. And that will be a big problem. Yes. So should not start a fire with this one. Even magnesium fires, you can't put carbon dioxide also. Even if you have carbon dioxide also react with magnesium. And it can brighten up the flame. You have to be very careful with that. 54, that is why. So it can react and evolve, evolve hydrogen gas that can explode. Did you understand that? Right. I hope you got got the thing. How can we put out a fire like that? There are other materials to put the fire like this. For this kind of fire, you have these various types of other fire extinguishers. You have various types of chlorofluorocarbon kind of material. Those kinds of other fire extinguishing methods are there. But you can't put water. It's like, when you have a fire because of oil, like, let us say some kind of coconut oil or something like that, you can't put water to this. It will splash the fire and you create all kinds of problems. There are various types of other methods also to use various other chemicals, forming material that you can use to extinguish a fire, but should not use water, right? Should not use water. I hope all of you got the idea. 54 is that, right? Now we will finish that tutorial. It's a good thing, right? Just to finish the tutorial. 55. So what are your thoughts on this? Now you all are better at it, right? Can we create a bomb with this method? Then I don't think that it has that. You might need a massive amount of magnesium. It's not that. Question number 55. Question number 55. Right. Yeah. Can we throw sand on top of burning magnesium? Yes, you can do that. That I think you can burn. Right. When hydrogen gas flamed, is it a light blue color appear? Mama hitanne. Hydrogen flame is it's giving water. So maybe there is excitation. Acetylene gives you a blue flame, but hydrogen, I don't think you get a blue flame. Right? Right? We'll think about it. I'm not sure. Right? 55. Lithium, sodium, potassium, rubidium, cesium, francium are stored immersed in hydrocarbons. Briefly explain the reason for this. But then no, we discussed this earlier also. Tell me what is the reason for you to keep it like that, right? What is the Yeah, can't use carbon dioxide to extinguish. Hurry. Now we'll go away from the magnesium fire, right? And there are some better things. Why are we storing these ones in hydrocarbons? To cut off, to cut off what? Cut off oxygen and water vapor and from reacting it, from reacting. So why are we use hydrocarbons? Hydrocarbons are non-reactive. Non-reactive solvents. And the metals have a higher density. Have a higher density so that it will sink. Higher density, it sinks to the bottom. To the bottom. HRI. No, no. Did you all understand that? Clear? Ah, yes. Highly reactive, very reactive. Right. Okay. So this is the reason. Question number 56. Look at the right balance chemical equation for the reactions taking place when the following metals are burned in air. So what will happen? When you use sodium react with oxygen, it immediately gives you the peroxide, Na2O2. Other than the peroxide, it can give you the oxide as well. Na2O. So this is 2, 2 times 2, 4. Next one is potassium. What will happen with potassium? Potassium plus oxygen gives you superoxide, KO2. And then you can have the peroxide also, K2O2. And then potassium can give you the oxide as well, K2O. So these reactions can take place. I hope all of you got that. Lithium react with nitrogen also. Say that they react with atmospheric gases. No, Chemeve. When you add water vapor, it gives you that, right? It's not that, right? When lithium reacts, when lithium reacts with nitrogen, when you heat it, just when you keep it, it won't react with nitrogen. It won't react with nitrogen. Clear? So it won't react with nitrogen. Everybody understood that? Right, okay. Everyone, is it clear? Right. 2 sodium, what? 2 sodium, 2 sodium, yes. Okay, yeah, right. You're in a balancing equation, right? Okay, fine. All of you got that? Right. What is the next one? Give the oxidation state of oxygen in the each species formed in the A above. What are the oxidation states of this one? If you look at the oxidation states, let us look at this one, oxide. Oxide is -2 oxidation state. If you look at K2O2, O2 2 minus, O2 2 minus means what is that? Oxygen, oxygen, right? O2 minus is like that, negative. Negative. And this one has a -1 oxidation state. Maybe oxidation state take a -1. And if you look at the O2 minus, it is like this. O, O. 1, 2, 3, 4, 5, 6. Negative. And here 1, 2, 3, 4, 5, and 6. So here the oxidation state is 0. Here the oxidation state is -1. No, no. Did you understand that? Oxidation states are varied like that. Right? Everybody okay with this? Anything else? Anything that you need to understand? Right. Yes. Right. Next one. Question number 57. How would you qualitatively determine the presence of nitrogen in the atmospheric air? Explain using relevant balanced chemical equation. How do you show that there is nitrogen? Qualitatively, not quantitative. You don't want a number. But you need to show that there is nitrogen present. So how do you do this? Take magnesium. Like, somebody asked me this, the reaction, magnesium. And what you do is you place it in some kind of a crucible and you burn it in the atmosphere, right? You can heat it and allow it to burn. So it burns. What will happen? Magnesium will react with oxygen. It gives you magnesium oxide. 2MgO, 2Mg. Magnesium reacts with nitrogen and it gives you magnesium nitride. Mg3N2. 2 here, 3. So this reaction takes place. It gives you this white powder, magnesium oxide, magnesium nitride. But then they are not colored. Now, how do you show that there is nitrogen in the atmosphere? What you do is you add water to this. When you add water, magnesium oxide plus water gives you magnesium hydroxide. Magnesium hydroxide. That gives you white precipitate. That is, there's no new thing here. Magnesium nitride plus water, what would you get? You get magnesium hydroxide and ammonia. Magnesium hydroxide and NH3, ammonia there. So 3 magnesium hydroxide, 2 ammonia, 3 times 2, that is 3 times 2, 6 vendati, 6 volt. Right. So ammonia gas evolves out. This gas evolves out. Ammonia gas evolves out. Now you can use, how do you distinguish ammonia? How do you identify ammonia? What is the method to identify ammonia? Using an HCl stopper. You use a HCl stopper and interact this. Use HCl stopper to detect. Use HCl stopper to detect. Now you can say if there is ammonia evolved, ammonia, where does it come from? It should come from the atmosphere. That means atmosphere, there is nitrogen. That's all. Did you understand that? Yes, Nestle's reagent or litmus paper. I think Nestle's reagent also works better. Really good white smog appear in this case. But Nestle's reagent, light yellow color turns into a brown color. And that confirms that there is ammonia evolved. Where do you get nitrogen? Now, you can't have nitrogen in magnesium. How do you get the nitrogen in the magnesium? You should get it from the atmosphere. So in the atmosphere, there is nitrogen. Right? Okay, question number 58. Let's read that question. Right? Let's see. Write balanced chemical equation for the reactions of the following species with water. Lithium metal with cold water. It gives you lithium hydroxide. So write down the reaction. Lithium plus water, lithium hydroxide, it gives you the product slowly and hydrogen gas is evolved. So this is 2, this is 2 and this is 2. Lithium hydroxide and hydrogen. Sodium metal with cold water. Sodium plus water gives you what? Sodium hydroxide, NaOH, and then hydrogen gas. 2 here, 2 here, 2 here. Beryllium with cold water. Beryllium with cold water. What will happen? No reaction at all. There's nothing is going to happen. Magnesium with cold water. Magnesium, and if you add water, again no reaction, right? Magnesium also no reaction. Magnesium with boiling water, what will happen? Magnesium not with steam, this case boiling water. So this is in the liquid form. So it gives you, what does it give you? Magnesium hydroxide plus hydrogen. Magnesium with water vapor, you know that. Magnesium plus water vapor, gas, it gives you the magnesium oxide plus hydrogen gas. Double check your answers. Calcium with cold water, calcium is reactive. Calcium with water, it gives you calcium hydroxide. plus hydrogen. Strontium with cold water, strontium with hot water. H2O liquid, hot water, again strontium hydroxide. It doesn't give you the oxide, hydrogen. Is it clear? Right. A magnesium hydroxide is MgOH twice. Right. Yes. Very good. Very good. Right. Okay. Question number 59. This is the last question. Then we can finish this. Write balanced chemical equation for the reaction of magnesium with the following acids. We have given a reactions earlier also. This also gives you a help to kind of remind those reactions. With dilute HCl, magnesium dilute HCl will react as a normal acid. HCl, it gives you magnesium chloride, MgCl2 plus hydrogen gas. Make it big, right? That's the first one. With dilute sulfuric, what happens? Magnesium with very dilute sulfuric, that also works as an acid. Magnesium sulfate will form, hydrogen gas is evolved. With dilute nitric means 50% nitric. It doesn't say very dilute. Magnesium nitric. Can you tell me what the product is? Magnesium and nitric, it gives you magnesium nitrate. What else? Plus nitrogen monoxide plus water. Balance it. Here it is 2. Here it is plus 5 to plus 2, 3 electrons. Multiply this by 2. So multiply this by 3. 3 and 3. 3 times 2, 6 plus 2, 8. 8 nitric means 4 water. I hope you all got the idea. Concentrated HCl, any HCl is acting like an acid, HCl. Magnesium chloride, hydrogen. 50% dilute sulfuric is just dilute sulfuric, same thing, right? 50% sulfuric gives you magnesium sulfate plus hydrogen. Concentrated sulfuric, what will happen? Magnesium plus concentrated sulfuric, what would you get? Can you tell me what are the products? It gives you magnesium sulfate. What else? Sulfur dioxide. What else? Plus water. This is how the reaction works. Now, sulfur dioxide is given, right? So magnesium to magnesium plus 2 make up the plus 2. So therefore, this is 2. 2 times 2, 4. This is also 2. 4 times 4 plus 2 is 6 plus 2 is 8. So that is the end of that tutorial. Right? Any questions to ask here from this material? Anything? What about C? It says dilute nitric. C with dilute nitric is 50% nitric. Dilute nitric is that. Okay. Is it clear? Any questions? Dilute nitric doesn't give you hydrogen. It is very dilute nitric acid. මේ dilute nitric කියලා කියන්නේ 50%. ඉතින් අපි ඔක දැන් තුනක් සැරයක් කිව්වනේ. Right? 50% dilute nitric is 50%. That is what it means. Very dilute nitric acid is this one. Question number 44, we haven't done it yet. I have marked it. Question number 44, we haven't done it. All the things that we need to understand that we haven't done. Once I finish the energetics, I will do this. Don't worry. I will do that once I finish energetics. Energetics, hopefully next week we should be able to finish that. We can start the energetic tutorial. So next one is starting from next week. I will start working on the energetic tutorial. Energetic tutorial, I have given answers. Most of the answers are right. But we will go through them slowly, gradually. We will work on this. I will start this tutorial. Right? Okay. And then group 15 tutorials I have given. You put the like with the answers. I want you to go through them. Right? Okay. Now we will look at the next one. The ඔතන තියෙන පුතා you have what about this කියලා තියෙනවා. It is a dilute nitric කියලා කියන්නේ. It's very dilute nitric acid. Here dilute nitric means 50%. Right? Right. Okay. Shall we look at the chemical calculation tutorial? So chemical calculation. Then we have to remember, I will never give up on this tutorial. We have to go it. Because when you do this properly, you will understand that it will help you in a bigger way later on. Right. Question number 7. Page number, no, not page number. This is the tutorial number 8. 7 we discuss everything there. Tutorial number 8, I think we are at question number 7. Is it clear? Right, okay. Are you sure? Everybody? All of you okay with that? Right, okay. Right. Question number 7. The reaction of finely divided aluminium and iron 3 oxide is called thermite reaction. The thermite reaction is a very important reaction, especially when they are welding various types of railway tracks. Like you can weld using iron. This is a very important reaction. It provides a tremendous amount of heat, making the welding of railroad tracks possible. The reaction of 750 of aluminium and 750 grams of this produces 247.5 grams of iron. Calculate the mass of iron that should be released by this reaction. What is the percentage yield of the iron? So let us see how this reaction works. Now you know Fe2O3, iron oxide, and you add aluminium to this. Aluminium gives you Al2O3. And this gives you iron, Fe. Right? So Fe is 2, Al2 is 2. So this is the reaction that is taking place. Right? The thermite reaction, 750 grams of aluminium. So you use 750 grams of aluminium. And 750 grams of iron 3 oxide. So this is also 750 grams. So this means we need to come up with the what is the rule here? What are the things that we need to come up with? We need to come up with what? Can you tell me? What are the things that we need to come up with? We need to come up with what? Can you We need to come up with the what is the thing that we need to work on? The theory here. If you have all the two materials given, what is the thing that we need to come up with? Can you tell me? It is the, rice chart, tamai, but what is that? It is the limiting reagent that we talk about. Yes, number of moles and the limiting reagent. So we need, without the limiting reagent, you can look at this. So number of moles is equal 750. Can you tell me what is the molecular mass of Fe2O3? What is the molecular mass of Fe2O3? 56 times 2 plus 16 times 3, 48. Here the 160 grams per mole. So what is that? 750 divided by 160 is 4.6875. 4.6875 grams. Did you understand that? So this is the number of moles of Fe2O3. What is the number of moles of aluminium? Aluminium is 750. Atomic weight is 20? 27 grams per moles. Atomic weight. So 750 divided by 27. Again, 27.7. Is it clear? Everybody understood that? Yes. Very good. So now we need to understand what is the limiting reagent. Can you suggest the limiting reagent? Can you suggest the limiting reagent? Right? So if one of these moles to react, you need to have 2 moles here. Right? Yes. So let us say limiting reagent is Fe2O3. So all of that Fe2O3 reacts. If it is the limiting reagent, it should react. So you need double the amount of material. What is the double the amount of material? 4.6875 multiplied by 2. Here the 9.375. 9.375 moles needed. Do you have it? Do you have 9.375 moles? But again, right? Do you have 9.375 moles? Yeah. It is you have more than that. 27.7. Again, this is right. This is the limiting reagent. This is the limiting reagent. That is true. Limiting reagent is that. All of Fe2O3 react. All of Fe2O3 react. And we need to calculate the amount of Fe that you get. Not grams, these moles. Amount of Fe that you get is number of moles of Fe that you get is double the amount. 4.6875 multiplied by 2 moles. You should get. 4.6875 multiplied by 2 is 9.375 moles you should get. What is the mass that you should get? Mass of Fe that you should get? Number of moles times the molecular mass. Again, 9.375 multiplied by 56 grams is equal to 525 grams. 525 grams you should get. Did you understand that? This is the number of the mass that you should get. Right. Okay. Good. Right. So many of you have got the answer. Good, good. 525 grams. And what do they say? What is the percentage yield of iron? I think theoretically you have to get 525 grams. But when you do this practically, you got 247.5. Practically, what is the percentage? Percentage is equal to 247.5 divided by 525 multiplied by 100%. It gives you 47.14%. හරිද? ඕක මොනවත් හොර කරන්න නැතුව කරන්න ඕනේ. එතකොට තමයි very easy. Right? Why does the question give 247.5 grams mass? Then when you do this practically, that is what the mass that they have got. Right? So in order to calculate the percentage yield. Did you understand that? Okay. Okay. Right? You need to look at this. Right. Let us look at the question number 8. Question number 8, whether we can do this. Question number 8. See whether we can work it out. Question number 8. A solution contained oxalate and carbonate ions. So, no, right? Oxalate and carbonate ions are there. Then you have oxalate, C2O4 minus. Then you have carbonate ions also there, CO3 2 minus. A 25 milliliter portion. 25 milliliter portion of this solution was treated with excess calcium nitrate. Excess calcium nitrate then. You add calcium nitrate, CaNO3 twice. What would happen? You know calcium oxalate is a precipitate. Calcium carbonate is also a precipitate. So what would happen? Calcium oxalate will precipitate. Calcium carbonate also is a precipitate. That also gives you this. So this is solid, this is also solid. So it gives you the oxalate and the carbonate you would get as a precipitate. Right? Okay. Completely precipitate both ions. The precipitate so obtained after drying has a mass of 0.820. Right? Make a mass. If you look at that entire mass, that mass has a value of 0.820 grams. Right? 820. That this is the total mass. Then don't worry about the earlier question. Right? You can look at the recording if you want. And now focus on this. Right? 820. Total mass is 820, 0.820. The precipitate was then dissolved in dilute sulfuric. Sulfuric. So when you add sulfuric, what will happen? It gives you this oxalate ions. They all dissolved. Oxalate ions gives you oxalic acid, H2C2O4. But they're not. It's important to look at this calcium plus oxalate C double bond O, C double bond O, O minus. O minus. O many ionic compound. So now what will happen is when you add H plus, may bond this bond is going to break. Right? This negative charge is gone, and you get a OH here. Then OH. And calcium goes with sulfate. You get oxalic acid. Oxalic acid. Oxalic acid. Carbonate. What happens to the carbonate? When you add sulfuric, it turns into H2CO3. H2CO3 can carbon dioxide ion. So you get only oxalic acid. Carbon dioxide evolves out. And you get calcium sulfate. Calcium sulfate and oxalic acid you get. The precipitate was then dissolved in dilute sulfuric and titrated with 0.05 molar potassium permanganate. 0.05 molar KMnO4, you use it and you titrate it. The titration required 20 milliliters. Try only. Calculate the concentration of oxalate and calculate the concentration of carbonate ions. But first tell me whether you understood this question. Anyway. Understood? Did you understand what they have done? What are they doing? Did you understand that part? Right? Is it clear? Right? Did you understand what have they done? Not quite. Hari, මොකක්ද ඔයාලට තේරුන්නේ නැත්තේ? Okay, very simple few sentences. මට කියන්න ඕනේ what is the part that you didn't understand here? Again, you have oxalate and carbonate, both ions are there. Right? Oxalate and carbonate ions are there. You add calcium nitrate to it. What is the calcium nitrate to it? Calcium nitrate, when you add calcium nitrate, you know calcium oxalate precipitates. Group 2 oxalate, calcium oxalate is a precipitate. Calcium carbonate is also a precipitate. Now you get the precipitate. When you add sulfuric, the calcium oxalate turns into oxalic acid and calcium sulfate. What happened to calcium carbonate? Carbonate ions always react with acids. Calcium carbonate, you get sulfuric. What will happen? Are sodium carbonate titrations and all that? What happens? Calcium sulfate. Calcium sulfate. What is the next one? Hydrogen and carbonate, H2CO3. H2CO3 turns into water and carbon dioxide. It turns into water and carbon dioxide. Carbon dioxide is a gas, it evolves out. What there another? Right? Did you understand that? Without understanding that part, we can't do the calculation. Okay, Salama, you need to kind of understand. Are you sure? Everybody? Because we are gradually going into exam questions. Past exam questions. Right? And you can see, if you go to the next tutorial, they are very lengthy. And if you look at them, they are also exam questions. Gradually, I'm diving into the deep end. If you have difficulties, you stop me and ask whatever the problem you have. How did they shape the? Did you understand it? Everyone? Is it clear? Any questions? Yeah, okay, right, fine. Now, right, okay. So, carbon dioxide gone away. Now, only thing that is there is oxalic acid. When you titrate it with potassium permanganate, oxalic acid and potassium permanganate react with each other. Reaction for the titration. Nah? So you have oxalic acid H2C2O4 and then MnO4 minus. MnO4 minus turns into what? Mn2 plus. Oxalate turns into CO2. This is plus 3. This is plus 4. Plus 3 to plus 4. How many electrons? 1 electron. There are 2 carbon atoms, so therefore 2 electrons. Permanganate to Mn plus 2, plus 7 to plus 2, you have 5 electrons. Make a multiplied by 5. This one multiplied by 2. So, this is 2. This is 5. This is 10. Right. How many H pluses? 2 times 2, 4. Again, another 6H plus. Right? 6H plus 5 times 2, 10. That means you have 8 H2, 8 times 2, 16. 16. Did you understand that balance equation? Balance equation, is it okay? Any parts that you didn't understand? Right, okay. Are you sure? Right, okay. So I'm going to tidy up this one, right? Tidy up the equation a little better. So I'm going to erase some of these parts there, right? And then this one also we will tidy up it little better, right? And then take it onto this side, right? This one is here. Right, okay. So that is in one line now. Okay, I hope all of you understood this. Right. මොකද්ද no sir කියන්නේ? ඔයාට reaction එක තේරුම් නැද්ද? What do you mean by no sir? No sir කියන්නේ මොකද්ද reaction එක? You didn't understand the reaction. This is like oxalate potassium permanganate reaction. Right, okay. Then අපි යන්න ඉස්සරහට. Right, okay. So we can identify, we can calculate the number of moles of oxalic acid present. කොහොමද කරන්නේ? Number of moles of H2C2O4 divided by number of moles of permanganate. What is the stoichiometry? Oxalic acid is 5, permanganate is 2. What is the number of moles of H2C2O4? H2C2O4 is equal to 5 divided by 2 potassium permanganate. Here the 0.05 times 20 milliliters. 0.05 times 20 milliliters, 10 to the power minus 3 moles. So 2 and this is 10. What is the amount? 5 times 0.05 times 10, 10 to the power minus 3 is equal to 2.5, 10 to the power minus 3. So what is the amount of oxalic acid that would have been present? 2.5, 10 to the power minus 3 moles were there. Okay. I have told no doubt. Sorry. Thank you. 2.5, 10 to the power minus 3. That is the oxalic acid amount. If you know the oxalic acid amount, you know the oxalate ions. May oxalic acid, if you want to get 1, you should have had calcium oxalate also 1. Number of moles of calcium oxalate that would have been there is also the same. 2.5 10 to the power minus 3 moles. Ne? Then you know the total weight of calcium oxalate. Total weight of calcium oxalate, you know me. Look at the laser pointer make me. 0.820. That is the total weight of calcium oxalate. Right. Let us look at the mass. Mass of calcium oxalate. CaC2O4. Here then 2.5 10 to the power minus 3 moles multiplied by calcium oxalate molecular mass. What is the calcium oxalate molecular mass? 40, 24, 64, 128 grams per moles. This is the number of moles of calcium oxalate present. 128 times 2.5 10 to the power minus 3. 0.32 tamai weight. Calcium oxalate weight is 0.32 grams. Right. Total weight is 0.82. What is the mass of calcium carbonate? Mass of calcium carbonate. What is the mass? Total weight is 0.82 minus 0.32. Here, 0.5 grams. What is there? 0.5 grams. Yeah, right. Good. I hope all of you understood this. Right? Why don't we take calcium sulfate for titration? The calcium sulfate doesn't undergo titration. Sulfate is in the maximum oxidation state, +6. I කොහෙටත් යන්න බෑ යාට. Potassium permanganate is oxidizing agent. මේ තියෙන දැන් +6 වල ගිහිල්ලා තියෙන්නේ. So it can't oxidize. හරි? Oxalate විතරයි. අර උක මම අර පොඩි චූටි කොළවල ඒ කාලේ අර when we are writing looking at the titrations we discuss those. ඒක බලන්න. ඒකේ මම summaries එහෙම දීලා තියෙනවා. Right? Please look at this. චුට්ට බලන්න. කමන්නේ. It's a good questions. You understand, right? So what is the number of moles of calcium carbonate? Number of moles of calcium carbonate is mass divided by molecular mass. 0.5 grams divided by 100 grams per moles. 0.5 divided by 100 grams per moles, 5 10 to the power minus 3 moles. Moles. Then what? Concentration of carbonate. What is the concentration of carbonate? Number of moles divided by volume. Calcium carbonate 5 10 to the power minus 3 means carbonate also 5 10 to the power minus 3. 5 10 to the power minus 3 moles divided by volume. What is the volume? What is the volume? You have taken 25 milliliter portion. 25 10 to the power minus 3. Cubic decimeter. This and this cancels out. 5 and 25 means 5. Here then, 0.2 again. Moles per cubic decimeter. Is it clear? Carbonate is 0.2. Oxalate. Oxalate, you know that there is 2.5 10 to the power minus 3. We have calculated it here. So now you can calculate the number of moles. Number of moles of oxalate, C2O42 minus, is equal to, again, number of moles divided by volume concentration. Concentration of oxalate. Here, the 2.5 10 to the power minus 3 moles divided by 25 10 to the power minus 3. Cubic decimeters. Here then, 1 over 10. 1 over 10 is 0.1 moles per cubic decimeter. Then, did you understand that? Okay. So it doesn't have to be filtered in order for it to be titration. Eka filter karanna ඕනේ නැහැ. You don't have to filter because they don't interfere. Interfere වෙනවා නම් තමයි, right? This kind of a question. මොකද්ද කියන්නේ? Isn't it a problem we don't get practice? You can practice it. I have given you questions and we have discussed them as well. Most of the reactions are in the acidic medium. But of course, there are reactions in the basic medium, and they can ask. I think when you look at SPD also, we are looking at some of those reactions again. එතකොට ඔයාට practice එකයි. But if you feel like that there is a little bit of a lapse, I think ඒකට තමයි you need to practice. Those things you can practice. වන්නේ හිතනවා මේක මට මේ work it out. Right? Right. So these are all most of them are acidic medium because that is where the interesting questions are. Right? But there are some interesting questions in the basic medium also. So what is the other one? How much time should you take for that type of question? ඉතින් මේ වගේ question එකකට around 10 minutes of it කරන්න පුළුවන්කම හදා ගන්න ඕනේ. But then the questions become lengthier with time. You will see lengthier and lengthier questions. I hope you got the idea there. Right. Let us look at question number 9 as well. Well, again, I know we have learned a lot of questions, but in a reaction like above, calcium carbonate, sulfuric, forming the products of it is it like how many products are there for a particular reaction? Make it think we have learned calcium carbonate and sulfuric reaction. You understand the carbonate ions, carbonate and H plus reaction. We have done titrations also, many titrations, sodium carbonate, sulfuric, HCl titration. It's the same thing. So it gives you H2CO3. Carbonate is C double bond O minus, O minus. So you get two H pluses and you get H plus here, right? And then H2CO3. Here a reaction. That is why I always tell you not to buy heart the reaction, but understand what is going on, what is really going on there. So H plus and carbonate combine together and form H2CO3. H2CO3 is unstable. It gives you water and carbon dioxide. So remaining materials react. What are the remaining materials? Sulfate form sulfuric and calcium form carbonate. It's right. I think, right, yeah. So that's why I want you to do these kinds of reactions, engage, so that you you happen to collide with this and then understand gradually the theory. We are doing this and you will be able to learn. Question number 9. Density of an aqueous solution prepared using pure sodium carbonate was found to be 1.0212. You want to make a density. This solution has a density. Density is equal to 1.0212 grams per cubic centimeter. So it contains sodium carbonate. Calculate the concentration of this solution, assuming that the density of water at the very same temperature is 1. So water at the very same temperature is 1 gram per cubic centimeter, and there is no change in the volume due to the dissolution. Let us say you are taking 1 milliliter here, 1 milliliter here, and you have to add sodium carbonate to this. So you have pure water 1 milliliters, you add sodium carbonate, but there is no change in the volume. That is what it says. And the density has changed to 1.0212. Let us look at the mass of water. Mass of water. What is the mass of water in 1 milliliter? 1 gram. Mass of sodium carbonate containing aqueous solution. What is the mass of sodium carbonate containing aqueous solution? 1.0212 multiplied by this 1.0212 grams. Enan, can you tell me what is the mass of pure sodium carbonate? How do you get the mass of pure sodium carbonate? 1.0212 minus 1 gram. Subtract 0.0212 grams. නේද 0.0212 ඔන්න ඔච්චරක් දිය වෙලා තියෙනවා 1 milliliter. What is the number of moles of sodium carbonate then? Is equal to mass divided by volume. 0.0212 divided by 106 moles. මේක තමයි moles ගන්න. 0.0212 divided by 106. Again, 2 10 to the power minus 4 moles dissolved. Dissolved වෙලා තියෙනවා. Now, what is the concentration of sodium carbonate? What is the concentration of sodium carbonate? 2 10 to the power minus 4 moles divided by what is the volume? 1 milliliter. 1 10 to the power minus 3 cubic decimeters. Here then, 2 10 to the power minus 4 divided by 1 10 to the power minus 3 is equal to 0.2 moles per cubic decimeter. So, 0.2 moles per cubic decimeter. Did you understand that? Can you explain the question again? You had sodium carbonate, you have water, 1 milliliter of water. Right? You add sodium carbonate to this. Yes, when you add sodium carbonate, there is no change in the volume. The volume එකට මොනවත් උනේ නැහැ. තේරුණාද? Right? Volume එකට මොනවත් උනේ නැහැ. Everybody understood that? හරි. So, if you look at the mass of water, it is 1 gram. 1 milliliter. 1 milliliter contains 1 gram. These are intrinsic properties. It doesn't depend on the amount. You can calculate for anything, any volume. When you have 1 milliliter sodium carbonate aqueous solution, the mass is 1.0212. So there's a mass change. Why do you have a mass change? You have a mass change because you have added sodium carbonate. You subtract. And then divide by 106, you get the number of moles. If you know the number of moles, you divide by the volume, you get the concentration. It's right. Can we subtract the densities and take the mass? Of course, you can do that. The theory is this. Are it clear? Right, okay. 1 milliliter of water and 1 milliliter of sodium carbonate, final volume should be 2 milliliters. You are adding solid sodium carbonate, not 2 milliliters. Pure sodium carbonate. Right? Pure sodium carbonate. So you are adding it to 1 milliliter of sodium carbonate. Sorry, 1 milliliter of water. Not 2 milliliters. It's not a solution. You are adding a solid to form an aqueous solution. Right, okay. Then the second one is this. With the solution in one above in the burette. Again, may solution like a burette. Right? So this sodium carbonate is kept in the burette. What sodium carbonate? This sodium carbonate is kept in the burette. 0.2 molar sodium carbonate. Kept in the burette. In the burette, 25 milliliter aliquots of sulfuric were titrated using phenolphthalein as the indicator. So you have sulfuric H2SO4 using phenolphthalein as the indicator. The average of 3 appropriate endpoints was 12.5 milliliters. Calculate the concentration of sulfuric acid in the solution. Then sodium carbonate you add to sulfuric. Whatever the questions you have. Right. What are the questions? In finding the number of moles, you have put V instead of M. I think concentration is mass divided by number of moles divided by volume. This is the This is the number of moles. This is the volume. This is the concentration. මොකක්ද ඔයා කියන්නේ? Hmm? Not that above. කොහෙද පුතා above කියන්නේ මොකක්ද? Now mass divided by molecular mass. So this is M. ඒක හරිනේ හැබැයි but I have substituted 106. Right. හරි. Okay. So sodium carbonate, it gives you phenolphthalein and sulfuric. Right? හරි. So what will happen? Sodium carbonate, you add sodium carbonate to sulfuric. Now, so all that sodium carbonate immediately react. Whatever the material that you add immediately react. So sodium carbonate and sulfuric, H2SO4, it gives you sodium sulfate and what? H2O and then CO2. Did you understand that reaction? What then? Sodium carbonate plus sulfuric, sodium sulfate, water and carbon dioxide. Right? So what will happen when you add? This stoichiometry is 1:1. Number of moles of sodium carbonate to number of moles of sulfuric is 1:1. H2SO4 is 1:1. What do they ask? They ask you to calculate the concentration of sulfuric. Sodium carbonate concentration is 0.2 molar. What is the volume that you use? 25 milliliters. In the Buret 25 milliliter aliquots of okay. Sodium carbonate volume is 12.5 milliliters. Endpoint average endpoint is 12.5. Divide by sulfuric. What is the concentration of sulfuric? You use 25 milliliters. Is equal to 1:1. එහෙනම් බලන්නකෝ. Milliliters cancels out. 12.5 2. 2 කියලා කියන්නේ මේක 0.1. බලන්න එහෙමද කියලා. The concentration is 0.1 moles per cubic decimeter. Concentration is 0.1 moles per cubic decimeter. Right, okay. No. Sodium bicarbonate doesn't form because we are adding sodium carbonate to sulfuric. If you do it in the other way around, you get sodium bicarbonate. Then only the reaction is controlled. We are adding sodium carbonate into sulfuric. So when you add sodium carbonate, everything reacts and it gives you sodium carbonate completely react, gives you water and carbon dioxide. What is another? Now, like, I understand that there's a large quantity of H pluses. A lot of H pluses. Then ඔයා දානවා මේකට කාබනේට් එක. Right? So what will happen? Yeah, this one will react with this H, this one will react with this H. Completely react. You see the control reaction in the other way around, if you do it in the other way around. Did you understand that? Alicot is a volume. It's another name for a volume. 25 milliliters ample. Is it clear? Would it be possible to carry out the above titration in the same way using methyl orange indicator? If yes, what is the endpoint you expect? So the endpoint doesn't change because you are adding carbonate to sulfur. So no change in the endpoint at all. Right? So the answer is yes, you can do that. Yes. No change in the endpoint. No change in endpoint. Why? Because all the carbonate completely reacts. All the carbonate react completely. Did you understand that part? බලන්න ඒකේ මොන හරි if there are parts that you don't understand, you can tell me. මෙන්න මේක මට තේරුන්නේ නැහැ. Right? How do you find whether a reaction is redox? If it is a redox, there is a change in the oxidation state. Oxidation number, if there is a change in the oxidation number, then it is a redox. Otherwise, it is not a redox. Right? So that is how you identify that. Can you please explain the methyl orange part again? Like, whether you use the phenolphthalein, whether you use the methyl orange, we are adding carbonate to acid. So endpoint doesn't change. All those titrations that we have done in indicators, we had the acid in the burette and the carbonate is in the titration flask. Then only you're adding certain amounts, controlled amounts of H plus. Then what will happen is carbonate goes into bicarbonate. Bicarbonate goes into carbon dioxide. If you add a little bit more. That's why you have two endpoints. But here you have H plus in the medium, in H plus in the titration flask, and you are adding carbonate into it. There is so much of carbonates for both of these oxygens to react. We are not controlling. Did you understand that? So endpoint doesn't change whether you use phenolphthalein, whether you use methyl. Everybody understood that. Yeah, what is the part that you didn't understand? Can you explain the methyl orange part again? That is what happens in whether you use methyl orange, whether you use phenolphthalein, it doesn't matter because you are adding carbonate to H plus, right? But if you do it in the other way around, then only the controlling take place. The indicator will change colors and the pH changes from here to here and from here to here when you have methyl orange and phenolphthalein. It is in the other way around. Here, this is where the HCl is, and this is the carbonate. Then only we are adding small amounts of HCl at a time. So carbonate goes into bicarbonate, bicarbonate goes into carbon dioxide. But here what you do is you have a reservoir full of H plus and you're adding carbonate into this. When you add carbonate into this, there are so many H pluses that are there. They will react completely. So there's no two different steps. There's only one reaction, always. Right. So question number 9 is also done. Right. Question number 8, 7, 8, 9 is done. Next week we'll look at the next one. Question number 10, 11, 12, 13. Otherwise, when you do too much also, you will have a difficulty. What would be our endpoint? 12.5. Make an endpoint. We know that 12.5 is the endpoint. Did you understand that? Right. Well, again, then in step 1, is there bicarbonate? No bicarbonates. No bicarbonates at all. Make a කිසිම වෙලාවක bicarbonate, you don't get bicarbonate at all because you are not controlling the reaction. Right? Did you understand that? There's a large amount of H plus, and when you add carbonate, it turns into then okay, let me remind you this again. Yeah. බලන්නකො whether you understand this. පොඩ්ඩක් ඉතින් අමතකත් වෙලා ඇතිනේ නේද? Carbonate. If you gradually add H plus, H plus දානවනම් තමයි, if you keep carbonate in the solution and if you add H plus, then මෙයා මොකද කරන්නේ? මෙයා H plus එක ගන්නවා and it turns into bicarbonate. Now we are controlling H plus. Control කරන්න මෙයා. Control H plus and you get OH here onto this one. And after that, if all the carbonate ions turns into bicarbonate, if you add more H plus, then you get H2CO3. But then I can't remember. I don't know whether you remember what my example was. I said that if the entire class was made hungry for 2 days, and then we bring a truck load of bread and ask you to get the bread, ask all of us to get some bread. We are still, you all are very obedient people, like, straightforward people. I told you that you will always go take one bread, and if everybody is fed, you go for the second bread, even though you have two hands. Right? So that is that. Yeah. So this is a controlled manner. You are giving the bread in a controlled manner. You are giving H plus in a controlled manner. So all of the carbonates Q on to turn this into bicarbonate. But if all of them are bicarbonate, if there is any more H plus, then it goes to H2CO3. Right? Let us say you have a lot of H plus and you are adding carbonate into this. Right? You are being asked to go into a room where there's full of bread. And you don't know whether there are other people at the back. So like that. So there's carbonate ions are the ones that you add into H plus. So this H plus will react, this H plus will react, and it turns into H2CO3. Right? If you add more carbonate, we don't know whether there is more carbonate. Right? More carbonate, those carbonates also will take H plus, and H2CO3 will form. Right? So you're adding carbonate into a place where there's large quantities of H plus. That's the difference here. Right? All this endpoint thing work when you add acid from the burette. If it is in the other way around, that is not going to work. Right, okay. So question number 9 up to 9 we have done. Next week we'll look at from question number 10 to 13. Right? Make sure to do this. I think that is why I'm doing these ones. Lazy, but then you will get stuck at a certain point. That is why. Right, okay. Right, Buddha, we will meet next week, right? Okay. So up to question number 13, 10, 11, 12, 13. And then we will start with energetics as well. Energetics, I will do odd questions, 1, 3, 5, right? Okay. And the answers are given, so you can try the even questions. Fine. Okay. Right. Okay. P block tutorials, I have given the answers. All written typed answers are given. I want you to do it and look at the answers. Man, right? I will discuss tutorials, P block tutorials. Once I finish P block, there's another set of tutorials. Those ones I will discuss. Right? Right. Okay, right. Okay, good night. Good night. Bye. Bye.